Math 287, Quest to College. I'm Joe Vasta, and we will be covering section 2.2, which is called Matrix Arithmetic. Your book calls it Matrix Algebra, but we're really doing arithmetic. Arithmetic being adding, subtracting, multiplying, stuff like that. So what we want to do is we want to take matrices and do arithmetic on them. So the very first thing that we're going to do is we're going to see how you multiply a matrix by a number. Sometimes that number is called a scalar. So let's go ahead and write this out. This is going to be 5 times this matrix. 1, 2, negative 3, 4, 5, negative 6. So if you were to come up with the rules on your own, maybe you can think about how you would define this scalar multiplication. How would you do it? Well, most of the time people think of the right thing to do. The scalar multiplication is defined by multiplying each element in the matrix by that scalar 5. So we end up getting 5 times 1, which is 5, 5 times 2, which is 10, and we just multiply. 5 times negative 3, negative 15, 5 times 4 is 20, 5 times 5 is 25, and 5 times negative 6 is negative 30. There's the answer right there. So we multiply by a scalar. We just multiply each element in the matrix by the scalar. So this is called scalar multiplication. I'll abbreviate. Okay, so that's one of the things we have to know how to do, is multiply a matrix by a number, a scalar. Now that scalar could be a complex number. Okay, so it doesn't always have to be real. In this class, most of the time they will be real. Now let's go ahead and do the next thing, which is called matrix addition. So I'll write that here. Matrix addition. So with matrix addition, let's go ahead and write these matrices down. We have 1, 2, negative 3, 4, 5, negative 6. We are going to add that to matrix B, which is 0, 4, negative 1, 3, negative 2, 5. So if you were going to think of what matrix addition is going to be, how would you define it? Well, the first thing that might trouble you is these are different sizes. Okay, this is a 3 by 2, and this is a 2 by 3. So to add two matrices of different sizes, if you try to do that, it's not possible. And if they ask you to do this in your homework, you're going to put undefined. And so the first one for matrix addition, sort of a trick problem. Adding two matrices of different sizes is not defined. So let's go ahead and do the next problem here. Let's go ahead and go A plus B. There's a capital T there. Remember, that stands for transpose. Okay, so A looks like this. 1, 2, negative 3, 4, 5, negative 6. And B transpose is writing the columns as rows. So the first column is 0, 3, so I'm going to write this 0, 3, 4, negative 2, negative 1, 5. And so this is how matrix addition is defined. probably in an obvious way, you add corresponding elements. So 1 plus 0 is 1. And notice the matrices are the same sizes, so we can do this. We have 2 plus 3 is 5. Negative 3 plus 4 is 1. 4 plus a negative 2 is 2. So this is a lot of arithmetic. 5 plus a negative 1 is 4. And 5 plus 5 is 10. Oh, sorry, did I say that? I said that wrong. Negative 6 plus 5 is, so I was looking at the wrong element. Negative 6 plus 5 is negative 1. So there is an example of matrix addition, one that works, and we have two matrices that are added together. They're the same size, they're 3 by 2s, and you get a 3 by 2 matrix as a result. Let's take a look at some of these official definitions, but really if you know how to do what I just did, you should be all right. Okay, so these official definitions look scarier than they are. Here's the index notation. A is Aij, and B is Bij, and S is a scalar. If A is an m by n matrix, then scalar multiplication is defined by this. S times A, you multiply each entry in the matrix, each element, Aij, by S. So that's how they define it. So it actually looks worse like this than just with an example. Matrix addition. If A and B are both m by n matrices, so they have to be the same size, then matrix addition is defined like this. A plus B, you add the Aij element with the Bij, and that becomes the new element for that position. Matrix subtraction, which we have not done yet, you have to have the same size. It's defined very similar. So let's go ahead and don't get bogged down on trying to memorize these symbol for symbol. Just try to do your homework. So here's matrix subtraction there. Let's go ahead and write this all out. This is 5 times A, 1, 2, negative 3, 4, 5, negative 6. And then we have minus B transpose. So B transpose, we just have that written above. Okay, so when you have scalar multiplication and subtraction, you have to do your order of operations correctly. Please excuse my dear Aunt Sally or PEMDAS, where multiplication is done first and then subtraction. So that's what I'm going to do when I do the multiplication. And the scalar multiplication, I end up getting something that we got like in problem 1, 5, 10, negative 15, 20, 25, and negative 30. And then I just copy this down. So at this point, it feels like this class is not as complicated as a Calculus 3 class, but it will get a little more complicated than this if you're getting a little bored with what we're doing here. So let's go ahead and subtract. 5 minus 0 is 5. 10 minus 3, 7. Negative 15 minus 4 is negative 19. 20 minus a negative 2, that's a positive 22. 25 minus a negative 1 gives me 26. And negative 30 minus 5 is negative 35. Here is our answer right here. Okay, so that completes problem number 4. We've covered matrix addition, matrix subtraction, and scalar multiplication. Let's go ahead and do the next problem. The next problem that we're going to have It's this one right here. We could actually multiply two matrices together. And so there's a definition for that. And so what I'm going to do is I'm going to go ahead and go A times B transpose. So this is 1, 2, negative 3, 4, 5, negative 6. And this one right here is 0, 3, 4, negative 2, negative 1, positive 5. So it looks like I learned my lesson and now I have the same size. So how would we multiply these together? Well, if you've never studied matrices before, you're probably already starting to multiply corresponding elements. But here's the deal. If you go to do this, you actually get undefined. Now, why would that be undefined? Well, we're going to actually get into the definition of matrix multiplication, and we'll see why that is undefined. So, let's move on and do a matrix multiplication where we're multiplying two matrices where it actually works. And as we do this, we'll go over the definition. So here it goes. So B times C. So B is really, look at this, this is a 2 by 3 matrix, and C is a 3 by 4. So we wouldn't be able to add B plus C, but somehow matrix multiplication is defined. And so what I'm going to do is write these guys out next to each other. So here is B, 0, 4, negative 1, 3, negative 2, 5, and then C goes right next to it. So this is what you'll be doing in your homework, and some of you have already seen this, like maybe in a pre-calculus class, though not all pre-calculus classes will cover matrices. So what am I going to do? To do matrix multiplication. First of all, this almost seems like you can't do this. Well, it's got a weird kind of deal. What's going to happen with the matrix on the left is you're going to run across the rows. So I'm going to picture like this little creature that all that creature does is run across the rows. Meanwhile, on the right-hand side, you're going to have a creature that doesn't run across the rows but drops down the columns. So I'm going to call that the column dropper. The row runner, the column dropper. Sometimes I'll call the row runner the road runner, and the column dropper the coyote. And if you don't know what I'm referring to, then you've got to get some culture. You've got to watch some of those cartoons. But here it goes. This is what I'm going to do. I'm going to point to both of those, and maybe I actually need another pin so I can do this. And I'm going to take those first two numbers. I'm running, Roadrunner is running across the first row, Coyote is dropping down the first column. And I multiply 0 times 1. So this gives me 0. Then I move over. They move over at the same time. So the Roadrunner moves over and the Coyote drops, and I go 4 times 3 is 12. And then negative 1 times 2 is negative 2. Now what I'm going to do with these three numbers is I'm going to add them together. And really I didn't need to put that plus there because I could have just said minus 2. This gives me the entry that is in the first row and the first column. Okay, so this is your first time seeing this. Whew. I mean, this is pretty intense. And if you've seen this before, you're probably really bored. Okay, the Roadrunner is going to go back over here. The Coyote is going to go to the second column. and you're going to multiply. 0 times 3 is 0. 4 times negative 2 is minus 8. And negative 1 times 4 is minus 4. Okay, so one of the things you might want to note is that I actually put the numbers right there. Why? Because on this matrix that I have right here, so let's just go ahead and go like this. This right here is the first row, which the Roadrunner is in, and the second column, and the Coyote's in the second column over here. So that's how I know. So the Roadrunner is going to go back to the beginning. He's on the first row, so I'm going to move over here, and Coyote's going to move to the third column. Hopefully we can learn how to do this a little faster, but I have 0 times 5 is 0. Minus 4. It's very high tech here with the pins. Minus 2. Roadrunner goes back. Coyote goes to the last column, and we have 0 plus 0 plus 3. Okay, now Coyote has run out of columns, so he's going to go back to the first column, and the Roadrunner is going to drop down to the second row. So look, this entry, I'm going to be second row, first column. So this is going to be 3 minus 6 plus 10. And I'm multiplying each time. Okay, Roadrunner, second row, Coyote, second column. You could actually do this without moving the pins. Let's see if we can do that. Watch this. 9 plus, oh no, I can't. Okay, I need to move, I'm just kidding. 9 plus 4 plus 20. Though it would be funny if really I got the wrong answer there, and then the Coyote's going to move over here. You have 15 plus 2. How did we get the plus 2? We went like that. And then we have plus 10. And then the last column here and the last row, we're going to get 30. No, what am I saying? 30. We're going to get 18 plus 0 minus 15. Whew, that was quite intense. There it is. So let's go ahead and write our answer. We don't have much room to write it. I'll write it right here. Looks like the size of the matrix for our answer is a 2 by 4. And so let's see, for our answer we're going to get 10 for the first entry, negative 12, that's this guy right here. Okay, and then this one right here, negative minus 4 minus 2 is negative 6. This is a 3. Down here we have 7, 29, 33, 25, 27, and then 18 minus 15 is 3. So we just multiplied some matrices together. That's going to be very important. I don't know if I can put a line there. Very important in this class that you multiply matrices together. Now, here's the deal. The whole reason this worked is because the number, see the Roadrunner is going across the row and he's going to hit 3 numbers, and the Coyote is dropping down the column, he's going to hit 3 numbers, and those were always the same, meaning the number of columns here equals the number of rows there. So what does that really mean? Is when you go to multiply 2 matrices together, and you put the sizes right next to each other, like B times C, those inside numbers have to be the same. Otherwise, it's not going to work. For instance, we'll go back to problem number 5. Here's the Roadrunner, here's the Coyote. We said undefined. Watch this. So, multiply 0, and then 8, and then Roadrunner crashes. And that never happens. And we shouldn't do that. There has to be enough numbers here. Now, if we had done a size check here, look, we have 3 by 2, and then this is 3 by 2. Those numbers, the inside numbers, are not the same. So that's why we can say undefined. Before, it looked like, you know, you're probably wondering, why did he put undefined? Because we didn't go over an example. And so now we'll always check the inside numbers and be able to answer undefined if those numbers are different. Now back to this, there's something else that's really sweet. The dimension, not the dimension, the size of our answer happens to be a 2 by 4. Okay, so that's good. But we can see that in advance by looking at these outside numbers, 2 by 4. And so those numbers will tell you the size. And that's good for planning purposes. You know, you don't want to make your brackets too big and then go, whoops, why did I do that? Okay, so that is the deal with matrix multiplication. Let's go ahead and do another one. All I've done for problem number 7 is I switched those guys around. So let's do a size check. C is 3 by 4, and B is 2 by 3. So what do you notice here about the inside numbers? They are not the same, which means this one is undefined. Okay, so that happens. There are sometimes you cannot multiply matrices together, and this is weird because with real numbers, you can always multiply real numbers together. Okay, you can go like 1 times 5 or 13 times 4.5, but here there are times when you cannot multiply matrices together. But the other weird thing is we were able to compute BC in the last problem. CB, that's undefined. So those guys are not equal, which tells us that matrix multiplication is not commutative. We've been living in a commutative world up to now. When you add 2 numbers or multiply 2 numbers, like 3 times 7 is 7 times 3, but with matrices, they are not. Matrix multiplication is not commutative. Matrix addition is. Okay, so B plus C, well, it's not defined here, but when we do matrix addition like A plus B, if you're able to do that, it's the same as B plus A. The other thing, some math people might like this. If you are going to multiply some matrices together, A times B, and you end up getting C, if A is M by N, and B is N by P, okay, so you can do it because the N's are the same. So let me just circle those. Then C is going to be M by P. Okay, so I've just did a typical math teacher thing and made something that you understand, made it more complicated by putting a more general thing. So, you know, math teachers do that. I guess we're supposed to do that. So what we're going to do is we're going to do a few matrix multiplications, and this is where I'm going to start encouraging you to do a few things when you watch these videos. So maybe, and some of you will do this and some of you won't, but hopefully most of you will. You've got these problems here. I would like you to pause the video and do the matrix multiplication in each of these problems. In fact, these two matrices are the same as these two matrices here, and I'm multiplying them in different orders. So pause the video and then see what you get. Okay, so let us go ahead and multiply these matrices together. Let's do a size check. This one is 2 by 2, and this one is 2 by 2. The middle numbers are matching 2 and 2, so we know we can do this, and the size of the matrix will be a 2 by 2. Those are from the outside numbers. So I end up getting 2 plus 15 is 17. And we end up getting -4 plus 9 is 5. So I'm like doing the Roadrunner and Coyote thing, but I'm using kind of my fingers. I'm not using the 2 pins. I have -4 plus 20 is 16, and then this one is 8 plus 12 is 20. Okay, let's go ahead and do this one right here. So I have 2 plus 8 is 10, and 6 minus 16 is -10. 5 minus 6 is -1. And 15 plus 12 is 27. So if you are watching these videos and your roommate is eavesdropping on you, but they're not watching the video, they probably think you are in a lower math class, because all I'm doing is saying arithmetic facts. And I knew the size check worked out because these are both 2 by 2s. So look at this in this example. You multiplied it one way, you got this. You multiplied it the other way, you got a different matrix. So this is just another example of matrix multiplication not being commutative. Now when you combine two square matrices that give the same result when you multiply, those two square matrices are said to commute. So sometimes you can find two matrices that commute when it comes to matrix multiplication. In the homework, they're going to define something called the commutator. Sounds kind of cool. Maybe you can call your next movie The Commutator. Is about some guy who goes and kills matrices or whatever. So you'll see that pop up in your homework. The definition is in your homework. Let's go ahead and do another problem here. In your homework, they're going to have you take powers of matrices. And whoa, what's up with that? How do we do that? Is this going to be 1, 9, 4, 16? The answer is no. When you have an exponent, it just says write 2 copies. So 1, 3, -2. 4 times 1, 3, -2, 4. So another matrix multiplication. You might want to pause the video and just practice this. Okay, so let's see what we get for our answer. End up getting 1 minus 6 is -5. 3 plus 12 is 15. -2 minus 8 is -10. And then the last one is -6 plus 16 is +10. So that's how you square a matrix. In the homework, they may even ask you to cube a matrix. The only kind of a matrix that you can put a power on happens to be a square matrix. So if you try to square, put the second power onto a 3 by 2, you'll line 2 3 by 2s up, and that will be undefined. Let's continue with more problems here. Actually, before I do that, here is matrix multiplication defined in the index format here. it says you have an m by n matrix and b is an n by p, then matrix multiplication is defined. So notice the middle dimensions n are the same. You don't have to actually, the middle dimensions are the same. You don't have to know this definition word for word, but here it is, AB equals Cij, where Cij equals, and there's a summation notation. This is you multiplying the numbers together and adding them. The Roadrunner is running across the first row and the Coyote's dropping down the first column right here, and then you just, you sum it up from 1 to n. So this is very abstract, but it actually describes exactly what we were doing in a mathy way. The size of AB happens to be m, there's that one, the outside dimension, by p. So there was the definition. It's on your definition sheet. Let's go ahead and do this one right here where it asks us to fill in the missing numbers. Okay, so what do we have here? We have 1, 3, negative 2, 4, plus some unknown matrix. It's going to be a 2 by 2 because that's how addition is defined. It has to be the same dimension. And you end up getting 1, 3, negative 2, 4. So what are we going to put there? Well, hopefully you could pause the video and figure that one out. You might be able to figure this one out as well. So for this one, you're going to put all zeros there. And you can see that if you do that, you end up getting something that's correct. Well, this matrix here has a special name. It is called the zero matrix for 2 by 2s. Okay, so the zero matrix is defined for all size matrices, has notation. Notation for the zero matrix is a 0. You can go 2 by 2, or if you're working in the realm of square matrices and it's obvious, then you can just go 0 with a sub 2 there. The definition here, the zero matrix is a matrix where every element is 0. This exists for any matrix. Okay, so for the 2 by 4s, you can imagine a 2 by 4 matrix where every element is 0. So zero matrix is a pretty simple concept. Now this matrix that we're doing right now, well, let's see. We have, what are we going to do? This kind of reminds you of arithmetic. So off to the side, I'll show you something. Look at this. If you had 7 plus some number equals 7, the number is 0. Sometimes 0 is called the additive identity. Okay, so this is kind of the same thing where you're going 7 multiplied by what number gives you 7. Well, we know that that number is 1. This is called, a little harder to say, the multiplicative identity. Okay, so what is the multiplicative identity? Well, if we're not really, if we've never seen this before, a guess that a lot of people do is they go like this. Let's just put 1s everywhere. So watch this. We have 1 plus 3. It doesn't work. Okay, so this is going to be a little bit more mysterious. How are we going to do this? Well, 2 of these entries are wrong, and I'm going to go ahead and wipe them out. If you happen to put zeros there, then let's check this out. We have 1 plus 0 is 1. 0 plus 3 is 3. Negative 2 plus 0 is negative 2, and 0 plus 4 is 4. This gives us the answer. And what is this matrix called? This matrix is called the identity matrix. For 2 by 2 matrices, there's the identity matrix. And the deal is, this is defined for square matrices only. Okay, and sometimes it has a name called I2. Okay, so what would I3 look like? I3 would look like a 3 by 3 matrix. And here's the deal, so you'll totally get it. It has 1s down the main diagonal and 0s everywhere else. So you can imagine what I4 looks like, and I27, etc. So it's time to look at our next definition. It says the identity matrix is a matrix with 1s in the main diagonal and 0s everywhere else. This exists for square matrices only. And that's going to be so important. So in the realm of matrices, you have the additive identity matrix and the multiplicative identity matrix. Well, which one's going to be more important? The multiplicative identity. So we're not going to call this the additive identity matrix and the multiplicative. This one's called zero matrix, and this one is identity. This is the identity matrix. The problem with the identity matrix, maybe it's a problem, I don't know. It only exists for square matrices, whereas the zero matrix exists for all different sizes. So this is going to be something you're going to see throughout linear algebra, and you'll see it in differential equations as well. Let's go ahead and do a few more problems here, and we'll hit you with 2 applications at the end of this lecture here. Okay, so here are some problems that you can crank out. You can pause the video and see if you can multiply those together and get a result. Okay, so let's do a size check on here. This is a 3 by 1. This right here is 1 by 3. So it looks like we can do this, and our resulting matrix will be a 3 by 3. So let's see if we can do this. So look, the Roadrunner and the Coyote don't have much running and falling. This is just 1 times 4 is 4. Okay. Now Coyote goes to the second column. 1 times 5 is 5. Coyote goes to the third column, and Roadrunner's sitting at the first row over here. 1 times 6 is 6. So essentially what just happened is when you have something like this, you just multiplied this matrix by 1. Then you got 4, 5, 6. Now I'm going to multiply this matrix by 2. You know, if you had scalar multiplication. So this is going to be 2 times 4 is 8. Then we have 10. Then we have 12. Now the Roadrunner drops down to the third column, and we have 12. And 3 times 5 is 15. And 3 times 6 is 18. And so there it is. We are actually multiplying a column vector by a row vector. So those are some fancy names for those. And we end up getting a 3 by 3 matrix. Let's go ahead and do problem number 14. This one is a 1 by 3, and this one is a 3 by 1. So the inside numbers match. My final result is going to be a 1 by 1. So what am I going to get? A 1 by 1 matrix. Okay, that seems weird. We have 4 plus 10 plus 18. So I'll write this middle step here. And so when we figure out what that is, it looks like 28, 32. And so there's a 1 by 1 matrix. So a few things to point out. The first thing is, what did it feel like you just did here? Maybe if you've taken physics or calculus 3. What you ended up doing was something that might remind you of the dot product of these two vectors. The second thing is, it's weird to have 1 by 1 matrices, but we really have been working with 1 by 1 matrices since kindergarten. Okay, so this is our 1 by 1 matrix. We won't see a lot of those, but when they come up, it's kind of cool. So that happens to be really what you're doing. We did matrix addition, matrix subtraction, scalar multiplication, and matrix multiplication. Is there matrix division? No, it's not defined. Not to say that maybe there's some math people off in some room in Europe and they say, let's define matrix division, but for the general linear algebra, we do not have matrix division, where we take one matrix and divide it by another. A few things to point out now. Let's see. Oh, wait. I guess we can look at this right here. The derivative of a matrix function, remember we looked at matrix functions, is obtained by taking the derivative of each element. So you're not going to have any problems assigned that have you to do that, but we're just kind of planting this idea, so when we get to differential equations, you'll go, oh, we can take a derivative of that. The antiderivative of a matrix function is obtained by taking the antiderivatives of each element. Here are some theorems. You don't have to memorize these. A transpose transpose equals A. Okay, and that seems pretty obvious. But if you were a math major taking a linear algebra class designed for math majors, maybe at the university, you would actually do formal proofs of these. A plus B transpose is A transpose plus B transpose. And then the last one that's kind of weird is A times B product transpose is equal to B transpose A transpose. And that one is a little weird. Why did they switch orders? Well, if you don't really want to look up a rigorous proof on this, because I'm not going to do any proofs, I don't want to start making this class be all proofs. You could actually just multiply two matrices together, maybe in your homework, and then take the transpose, and then go ahead and do that, multiply it, and see that you get the same thing. Okay, so these are just some theorems you'll see in linear algebra, but you don't have to memorize. Another theorem, the product of two lower triangular matrices is lower triangular. And the product of two upper triangular matrices is upper triangular. Okay. Let's go ahead and show you a few other things here. So look at this. In algebra, when you have a plus b squared, it's a plus b times a plus b, and you multiply them out and you do a FOIL, and lots of times you could just put those together and write that as 2ab. But in the world of matrices, you cannot do that because matrix multiplication is not commutative, so that's as far as you can go. Here's something else that you can just ignore, just like this here. I mean, hopefully you see why you don't want to simplify that with matrices. So here's something else you could just like skip ahead on and not look at this, is the formal definition of the identity. Now, if you remember the definition that I did, it was it said all ones in the main diagonal and zeros everywhere else. It's not that technical. This is more technical. This is called the Chronicler delta symbol. And it is delta I, j, and it's 1 when I equals j and 0 when I does not equal j. Also, lots of linear algebra books will say, well, then the identity, I sub n, that's the element. This is the index notation, so this is the same ones down the diagonal and zeros everywhere else. So that is, I think, all that we have to do here. The rest of this lecture will be two applications. I mean, this matrix multiplication was defined really crazy, so why would it be defined crazy? I mean, is there an application that would make more sense of what we've been doing? And there are actually two applications that I'm going to show you, but there are many applications of matrix multiplication. So we'll turn it over to the PowerPoint. First application of matrix multiplication happens to be something that you can use in the business world. This matrix right here, which is a 3 by 2 matrix, represents the fruit sold by a company at 2 farmers market locations. So the two locations are Vectorville and Mathington Beach. So at Vectorville, they sold 200 apples that day, 50 oranges, and 80 bananas. Meanwhile, in Mathington Beach, they sold 100 apples, 70 oranges, and 120 bananas. Okay, so this matrix holds how much stuff was sold and what kind of things were sold at each location. The next thing we're going to bring up is a profit matrix. The profit matrix tells you the profit from each item. So I'm just a math teacher, so I've made up these profits. But let's just say for every apple they sell, they get $1 profit. And then oranges give 50 cents per orange profit, and then bananas 80 cents. So we're going to illustrate matrix multiplication. We're going to go P times A. So matrix P times matrix A. You can do that because matrix P is 1 by 3 and matrix A is 3 by 2. Okay, so there's the multiplication. And this multiplication actually gives us something. Look, in Vectorville, they sold 200 apples. Well, 200 times 1 gives me $200. Meanwhile, 50 cents times 50 gives me the orange profit for Vectorville, and 80 cents times 80 gives me how much profit, how much money I made from bananas. And then because matrix multiplication, those get added up, and the 289 represents the profits from Vectorville. Whereas the 231 gives me the profits from Mathington Beach. I kept this example small, but in the real world, you can have like 75 different locations and hundreds of things that you sell. And all you have to do to get the profits from each location is a matrix multiplication. Let's go to our next example. The change in residents each year. Okay, so we have Vectorville, Mathington Beach, and none. Let's just say this is all within a county, so this is other places within the county. So it looks like Vectorville, from year to year, 70% of the people usually stay there. Whereas in Mathington Beach, it looks like 80% of those people stay there. So it looks like people like Mathington Beach better than Vectorville. And then other places in the county, 70% stay in those. But look at this. In Vectorville, 20% will move to Mathington Beach within a year. And then 10% will move to another place. Okay, so the 10 plus 20 plus 70 adds up to 100%. And then same here. So this diagram is, sort of like a flow diagram. I mean, we can do some graph theory on it. But it's very hard to grab. And it has probabilities in there. So what we do is we come up with a probability matrix, sometimes called a stochastic matrix. And this matrix, 3 by 3, describes this information right here. So look, from Vectorville, there's the from. To Vectorville, it's 0.7. And that describes this right here. From Vectorville to, so this is the from, to Mathington Beach is 20%, and there it is. So there's that 20%, and then 10% leave Vectorville to go to another place. And so this actually holds the probabilities. If you add up the entries in each column, they will add up to 1. Now that's not the case with adding up the entries from each row, but the columns add up to 1, and that gives you the probability. So let's look at something else. There's our stochastic matrix, or you could call it a probability matrix. Here's our state matrix. The state matrix tells us what is happening right now. So 15,000 people live in Vectorville, 20,000 people live in Mathington Beach, and 65,000 people live in other parts of the county. So here is the beautiful part. We're going to illustrate matrix multiplication again. We're going to go P times X. See, P is 3 by 3 and X is 3 by 1. And what we're doing is we're zapping each of these numbers with the probability. So like 70% of 15,000 plus 15% of 20,000 plus 15% of 65,000. You add those together, you get 23,250. That's how many people we expect to live in Vectorville after a year. And so this is done a lot in probability theory, where you have a probability matrix or a stochastic matrix and you multiply it by a state matrix. The funny thing about this whole example is this right here becomes a new state matrix, and if you want to find out what happens after 2 years, you would multiply this thing that I'm circling. You'd multiply it by P, and matrix P would be multiplied on the left. And so we'll show you what happens after a few years now. So this just reminds you there's a stochastic matrix and the state matrix. I didn't change those. And so p squared, that's like hitting it with 2 of the probability matrices. This is after 2 years. So numbers are changing, where Vectorville is on top, Mathington Beach is there, and then there's other. So let's see what happens after 5 years. So it looks like Vectorville is increasing in its population, and so is Mathington Beach and other places of the county. I mean, they're just moving there. After 10 years. And so the thing that you can do with this is take a limit as the years go to infinity, and this sounds like calculus, so I'll go p infinity x, and there's the limit. Now, of course, this is kind of weird to do. You really wouldn't want to use the model to say what's going to happen a million years from now, because things happen, and when maybe a factory closes down in Mathington Beach, that will change this stochastic matrix, or something happens. Maybe a big business moves to Vectorville, or whatever, a catastrophe, an earthquake. Those probabilities will change over time. But in terms of, the probabilities you have, and let's suppose this is all you had, this is your predictions, and you really don't want to go out 100 years. How did I get this limit? Well, a lot of people would guess, oh, we just did calculus. Well, we actually did a little more. We did something we're going to learn later in this class called eigenvalues and eigenvectors. So we'll actually come back to this application and see how I got those numbers there. That is our last application. This completes section 2.2. Make sure you keep up with the homework. You might be thinking, I'll just do the homework right before the test. You want to do the homework as you see the lectures, and you want to do them. You want to kind of space yourself out and not just spend 20 hours trying to do all the homework, because you'll drive yourself crazy. Well, you guys have a good day, and I know this is a little silly. I said it last time, but I'll continue saying this. I'll see you next time.